This conference will now be recorded. This conference will now be recorded.
Very good evening, students. We have been discussing previous year's questions from JEE Mains 6th September 2020 paper, and this is the second shift 2 questions. So we have already discussed few questions. Today we'll be discussing few more questions, and one more date I'll take to finish this, and then we'll go for the 21, 22, like that we'll discuss. Once we finish 21, 22, we'll go again 2020, 2018, 2015, 16, etc. Okay, so we are going in the descending order. All right, so today we have few questions, and this question is among them. Let us take this question and try to solve it.
This conference will now be recorded.
Good evening, students. We have been discussing PYQs from JEE Mains papers. So today we have some questions from 6th September shift 2 2020 paper. So let us try to understand the problem given here and then try to solve it. The question says two planets have masses m and 16m. So one is smaller planet, another one is a bigger planet. Their radii are a and 2a respectively. The separation between the centers of the planet is 10a. Let us draw this situation. This is one planet, and let us take the bigger planet to be this. This has 2a radius, and this has radius a. And this has got mass m, and this has got mass 16m. Okay, now their center to center separation is given as 10a. Okay, so this is the situation up to this. Now let us read again. A body of mass small m is fired from the surface of the larger planet. So I have, suppose, a small mass, an object having mass small m, which is just on the surface of the bigger mass, and it is fired from here. Okay, this has got small mass m. Okay, it is fired from the surface of the bigger planet or larger planet towards the smaller planet along the line joining their center. So this is actually fired from here like this. Okay, along the line joining the centers towards the smaller one. For the body to be able to reach at the surface of the smaller planet, the minimum firing speed needed is. So you have to find out the minimum firing speed. So how do we do that? Actually, we have to see, we have to give minimum speed to see. This is actually the mass m. You know, this mass is attracted by the bigger planet as well as the smaller planet. Okay, so this will be, so attraction on this will be, see, if I draw like this, so attraction by the bigger mass, let us say this is B planet and this is planet A. So this is force on this mass by A, and there will be force in this way also, force on the mass M by, sorry, this is by B and this is by A. The smaller one will have smaller effect and the greater one will have greater effect, obviously. But look, one thing we know, the gravitational force is Gm by r square. It varies as the inverse of the square of the distance. Okay, now if I take this object of mass small m along this line, suppose at any time I have brought this mass here, then what will be the force? The force actually will not be the same when it was at the surface. Now the force by the bigger one will be lesser, little lesser, at least when it was on the surface or near the surface it was greater because the distance was less. Now the distance has become larger, so force by bigger mass will be lesser. Again, this force by smaller mass will be little larger, even though it has got lesser gravitational pull, but it will have. So we'll see there will be a situation or there will be a distance where this pull, see, force on the mass m due to A and the force on the mass m due to B, these two pull, like the pulling forces will be equal and there will be no force at that particular point. If I just take that point to be, sorry, that point to be here, let us say this is the point P. Okay, I can just draw a line also like this. So this is the point. Okay, so point P where these two forces are equal and there will be neutral point here. Okay, why I am saying this? See, after this neutral point, you know, after this neutral point, this the pull, gravitational pull by smaller planet will be dominating over the gravitational pull by the larger mass. Okay, so at this particular position, if it is given sufficient amount of speed so that it can just cross this point P, then it will be easily pulled by this smaller planet, and there you no need to give any extra effort to make it to fall on the surface of this smaller planet. So first point will be to find out the neutral point where the gravitational pulling force by both on the object will be the same. I'm taking that distance to be x from the center of this bigger one. Okay, let us say this is x, and see their center to center distance was actually 10a. So this distance will be from the center, this distance will be 10a minus x. Now I can actually find out gravitational force at this point on this mass due to A and due to B both. Let us write and equate them, as I have assumed that neutral point will be the point P. So I can write, look what I can write, G small m, okay, capital M, divided by x square, that is the distance square. So this distance, let us say 10a minus x whole square, and the other one is say 16 m, so 16 gm small m divided by x square. So I can say gmm, these three quantities I can strike them out. Now look, I can just take the square root from both sides. Okay, on the both sides, then if I take square root and then simplify, okay, let me just take square root itself. So 10a minus x you will get here. Okay, if I consider just positive quantities, so this will be 4 divided by x. Now I can simplify and solve for x. X is equal to 40a minus 4x. Okay, so this will be 5x is equal to 40a. Then you get x is equal to 8a. Okay, this is what we get. X is equal to 8a. So that means this much is 8a. So rest of the thing will be 2a. Now I have got this thing. Okay, this point where, so x I have got, x is equal to 8a, and 10a minus x, that is this one, this distance is actually 2a. So once I get this, then rest what I can say, so look here, we have got now this mass to be here. Okay, here say this mass is, okay, I have drawn it a little bigger, let me make it smaller. So I have now my mass here, and this is here. Okay, so if I just give minimum velocity here, v minimum, such that it just cross this point. Okay, just cross x distance. X is equal to how much? This is 8a. So if I give that much of kinetic energy, then it will just eventually fall on the surface of the planet, smaller planet. Okay, so this can be, see, now here basically what we'll do, so it will just fall on this, so there will be no kinetic energy here. Okay, so this will be, v will be 0 here. Okay, while reaching here. All right, so there will be certain potential energy. Obviously at this point, let us take this situation. See, I have to apply here, actually by applying conservation of mechanical energy or conservation of total energy. Okay, so what we can write, we can write at this particular position, let me just first write at this point, let us say this is point 1 and this is, here it is point 2. Okay, so I have to actually apply total energy conservation. Okay, all right, so at this point, what is the speed given? Minimum speed half m v minimum, let us say that is v minimum is v. Okay, so half m v square, the total energy over there, and then what is the potential energy over here? So potential energy due to this B, okay, planet B will be GMM by A. A is the distance. Okay, this is 2A at this particular position. So GMM 16M GMM small m by 2A. So this is the potential energy, kinetic energy at this particular position due to, okay, so potential energy due to this bigger mass, but there will be some potential energy at this particular position due to the smaller mass also. So what is this potential energy? What is this that potential energy? So actually, okay, let me first write it, then we'll discuss. So the potential energy given by this will be, like, potential energy due to the smaller mass will be GMM by 8A. Okay. See what I'm saying. See, since this point is neutral point, I'm just actually considering that this, see, the potential energy from this point, okay, this point, I'm just considering that this is the point where the surface of this smaller planet is situating. Why I'm saying this? Because at neutral point, see, thereafter there is no force required. Okay, all right. So this is why I'm just taking this distance. Okay. Now again, at this particular position, so when it is just on the surface, that means, you know, you have to consider the potential energy up to this point due to this bigger one, and I will be taking the potential energy on the surface of the, okay. So look here, we have to do the calculation up to this neutral point. That is what I'm trying to say. So here there will be no speed because I'm giving that much energy, kinetic energy, such that it will be just crossing P, just crossing P. After that, there will be no speed at all. So there will be zero kinetic energy. And what are the potential energies? So potential energy on the surface of the smaller planet, sorry, divided by 2A, that is the, I'm sorry, that is A. Sorry, this is actually 2A only, because as I was saying, you have to consider the point P. Okay, consider the point P. This is 2A. And similarly, from here, I have to calculate potential energy at this much distance due to this bigger planet. So 16 GM small m divided by 8A. Okay, from the center. All right, so if we now simplify for V, what we are going to get? So up to this, what we have got, I'll just rewrite this. See, I have got half mv square, that is the kinetic energy. I have got potential energy due to the bigger mass when it was on the surface. This one, and potential energy will be there due to the smaller planet up to what? Up to 8 distance. Okay, that is equal to minus 16 gm small m a by 8a minus of gmm by 2a. Okay, so up to neutral point we are doing every calculations. Okay, so look now, if we simplify 16 GMM by 8A to A, so you can just write this 16 GM small m by A, so this is 1 over 2 minus, so if I just take this to that side or bring this side, this will be plus then, so 1 by 8. Let us take this to other side, so GMM by 1 over 8 plus 1 over 2, sorry, this will be minus 1 over 2. So here for this actually this will plus, this will be minus. If I am taking this common, so there will be minus over here. Okay, this is the one. And see this part, let me just calculate this one. So this will be 4 minus 1, so 3 by 8. Okay, 3 by 8. All right, so let us just erase this part. Again, here it will be minus 3 by 8. Okay, now if I take this all this together, half m v square 3 by 8, I'm taking this side, 3 by 8 gmm by a, so this will be 16 plus 1, I'm sorry, this 3 by 8 16. Okay, I think there is some issue here. Yeah, there will be minus sign over here, that is for sure. This, there will be minus sign here, positive. Okay, so I think this will be 15 here. Okay, there will be minus sign over here. Okay, so all right, so half m v square, so this calculation you can do, I think, better. Okay, so these two I can just strike them with this 4, this m I can strike out. Okay, so I have got, look what I have got, so 3, there will be another 3 over here, so if I just take square root, then you look, I'll get 3 by 2 here, then I'll get square root of 5 g capital M divided by a, so this will be the answer, 3 by 2 5 g m by a. So this is the answer for this first question. Okay, I hope you have understood this. I'll just repeat what I have done. See, just one point I just want to mention over here. So this, you might be thinking that why don't we go for directly conservation of energy. So in that case, you know, when you write conservation of energy, since their distances are, see, this is having 2a, this is, so these are actually, there will be effect of one on the other. Okay, that is where is the problem. So that's why you have to get a point where there is a neutral point. So that's why you say what we say at infinity potential energy will be 0. So that's how in case of escape velocity of the earth, we just directly apply the energy conservation. Okay, potential energy plus kinetic energy, and at infinity there will be potential energy, uh, energy will be 0, right? So that is what we do, potential energy at infinity will be 0 actually, or yeah, so that's how we go for the conservation of energy. Okay, Okay, so in this case, this point, neutral point, finding out the neutral point was necessary. Okay, so this is the answer. All right, so this problem is from fluid mechanics. Okay, so this is fluid dynamics. Let us read this problem. So this problem says a fluid is flowing through a horizontal pipe of varying cross section with speed small v meter per second at a point where the pressure is P Pascal. Okay, at another point where the pressure is P by 2 Pascal, its speed is capital V meter per second. If the density of the fluid is rho kg per meter cube, then flow is streamline. Streamline flow. Then what is the V equal to? So there are options here. See, this question can be easily answered using, let me just show you the situation, then you will get by yourself. So suppose there was a horizontal pipe, okay, horizontal pipe like this. So at some point, see, varying cross sectional area, okay. So varying cross section means there will be pressure variation also, and it is horizontal. This is where you will get the advantage. Okay, so here, see, at this particular position, speed is small v and pressure is P, and here pressure is P by 2 and speed of the fluid is capital V, so that it becomes a streamline. For a streamline flow, we can apply Bernoulli's theorem, okay, or Bernoulli's equation you can use. So what is that said? Kinetic energy head plus potential energy head plus pressure energy head will be constant. Okay, that is what is the Bernoulli's theorem. Okay, so here we can actually use Bernoulli's theorem. Okay, because the fluid is moving and it is a streamline flow, so pressure energy per unit volume is P at this particular position. Okay, let us say this is point A, and somewhere I am just taking this point B. So at these 2 points I am just applying Bernoulli's theorem. Okay, applying okay, so P pressure energy plus kinetic energy per unit volume, that will be half rho v square only. Okay, and the potential energy for both the places it will be the same, so that's why I'm not writing, because there is no height difference. Okay, so at the horizontal surface, let us take the potential energy to be 0, and here what is the pressure energy? P by 2, and what is the kinetic energy? Half rho capital, because rho is constant. Okay, so I can write this. Now look what we get from here. So I have to find out in terms of small v. I have to find out what? I have to find out capital V. Okay, so we get half rho capital V square to be P by 2 plus half rho small v square. So I can just divide with, so multiply with 2 first. So both sides I can just remove this. Then I can divide with rho. Okay, so V square, sorry, capital V. So let us write directly. V is equal to square root of P by rho plus V square. So this is the velocity at this particular point. Okay. So you look, the first option will be the correct answer. Let us go to the third problem. So this problem, as you see from the figure, it is from the chapter heat conduction. So heat conduction. Now let us read the problem. We have understood where the question has come from. Let us now read the problem and try to answer from there. Okay. So three rods of identical cross section and lengths are made of three different material of thermal conductivities K1, K2 and K3 respectively. So I have got, see, you can see from the figure that cross sectional area if A, then A for all of them. Okay, better to take some other ink. Let me take the ink blue. So area of cross section for all of them are same. You can see that. Okay, all of them are same. And lengths also, you can see all of them has the same length, L, L and L. Okay, so these are the informations given here so far. Now the question is, they are joined together at their ends to make a long rod as shown in the figure. Yeah, they have been connected. Okay, these three. One end of long rod is maintained at 100 degrees centigrade. After connecting them, I am getting a long rod, some 3L length, and say one end is maintained at 100 degrees centigrade temperature, and the other rod is, other end of the long rod is maintained at 0 degrees centigrade temperature. Okay, if the joints of the rod are at 70 degrees centigrade and 20 degrees centigrade in steady state. Steady state means the temperature remains constant at that particular junction or joints. Okay, there is no loss if there is no loss of energy from the surface by radiation. Okay, from the surface radiation can happen, so it is said that that is not happening here. So energy loss is not happening due to radiation through the surface of the rod. The correct relationship between K1, K2, K3 are. So I have to find out the correct relationship between K1, K2, K3. So where there are few options given here. See, K1 is to K3 is equal to 2 is to 3. K2 is to K3 is equal to 2 is to 5. And similarly, K1 is to K2 is equal to 5 is to 2. And K1 is to K3 is equal to 3 is to 5. And option C and D are showing the relation like this, whether K1 is greater than K2 greater than K3 or K1 is less than K2 less than K3. Okay, so see here, it is very simple problem. Here, you know, the total heat energy is conserved, right? Total heat energy is conserved. Total heat energy, which is flowing actually, will be constant. Heat energy flowing through each is constant. Through each rod is constant. This is actually the idea here or the concept here. Okay, if I say Q1 is flowing through this, Q2 is flowing through this, and Q3 is flowing through this, then all Q1, Q2 and Q3 are actually same. Okay, Now look how to get Q1 and Q2 or Q3. Okay, so that we are going to calculate now. Okay, so see, I can write Q1 equal to Q2 for this. C for this 2, I can write Q1 is equal to Q2. This I can write, and separately I can write Q2 is equal to Q3. That is what I can do. Okay, separately I can write Q2 is equal to Q3. Okay, fine. Now let us see what is Q1. See, the heat flow is actually directly proportional to the thermal conductivity, directly proportional to the temperature difference between the ends, and at steady state everywhere I think I just take average. Okay, average difference, like constant difference, temperature difference, and it depends on temperature, time, and the difference or the separation between the hot and cold ends. Okay, look, then see the expression for the Q is actually K into T2 minus T1, where T2 is greater than T1, into A into T divided by the length. Okay, like this. Now here I can write K1, the temperature difference, I can write 100 minus 70. Okay, then area, time, anyway let us take any time. Okay, anytime T, and length is some capital L. Okay, and for this also we know this only K2 is different, and temperature difference will be obviously different. See, for this actually you have temperature difference 70 minus 20 divided by, see, A into T into L. This is also L. So see, I can just strike out A, T and L. Okay, so ultimately what we get K1 into 30 is equal to K2 into 50. Okay, so now we'll get a relation between K1 by K2. K1 by K2, what we get? We get 5 by 3. So I'll check where there is 5 by 3, K1, K2. I see. I have to cross check these options. I think K1, K2, this is given as 5 by 2. It is not possible. So then maybe while typing this I have typed it wrongly. So K1 is to K2 is 5 by 3. So 5 is to 3. Okay. And see, so between 1 and 3, what will be the relation? Okay. So 1 and 2 we have got, then 2 and see K2 into, see this K2 I can write this 50 into K2 is equal to, this is 20 into K3. Okay, so K2 by K3, I'll get K2 by K3 as K2 by K3, I'll get 20 by 50, so 2 is to 5. 2 is to 5. Okay, let me just check here. So I have got K1 by K2 is equal to 5 by 3, and then we get K2 by K3 is equal to 2 by 5. Excuse me. So what is k1 by k3? So k1 by k2 I'll write like this, k2 by k3. So let me multiply this, then 2 by 5. Okay, so here I'll get k1 by k3 is equal to 2 by 3. I don't know whether it is matching. Okay, k1 k3, I think this is the option, 2 by 5, k1 k2, k1 k3, one option is okay, that is 2 2 3. So I have obtained 2 and 3 also. 2 and 3 I have got 2 by 5. Okay, 2 and 3 I have got 2, yeah, 2 by 5. So I think this one is the answer here. Okay, this A will be the answer. All right, so don't get confused, so you can do it better. Okay, so k1 is to k2, k1 is to k2, we had got 5 by 3. Okay, 5 by 3. If k1 by k3 is given in the answer, then check, it will be 2 by 3, and k2 by k3, which we have got 2 by 5. So which are the options given? So k1 k3, k1 k3 I should get 2 by 3, that is fine, and k2 k3 I should get 2 by 5. Yeah, that is also fine. So first option is the answer. Okay, all right, let us go to the next problem. This problem says, when a particle of mass m is attached to a vertical spring of spring constant k, the situation is something like this. Okay, okay, let me just draw it little better way. Okay, so this is a vertical spring having spring constant k, and release, see, it has got, say, a particle of mass m is attached. So after attaching a mass m to a vertical spring of spring constant k, it is released actually. Okay, it is released. See, the initial situation is something like this. See, if I have a spring of normal length, suppose this is normal length without any mass, and let us take this spring, as it is not said here, let us take that spring has mass 0 or massless spring, then a mass is attached, so there will be obviously certain displacement. Okay, certain displacement. Okay, so its motion, okay, it will not stop actually. After stretching this, there will be restoring force. Okay, so when it goes to the other side, then there will be pushing, like pulling and pushing force will be there by the spring, so there will be oscillation. Okay, there will be an oscillation. We are given that particular oscillation to be described by y is equal to, see, y of t is equal to y0 sine square omega t from the lower end, from lower end. Okay, this is the displacement from lower end. Okay, lower end means this. Okay, lower end means the length of the normal length of the spring from there to this. Okay, this distance is given. Okay, at any instant of time, it varies actually. So look, I have to check whether this is, see, the question is, then omega is equal to what? You have to find out the angular frequency. Okay, angular frequency you have to find out. We know, see, if this motion is somehow is proved that it is simple harmonic motion, then rest of the thing I know what to do. Okay, Then for a spring, see, for a small oscillation, sorry, simple harmonic oscillation with the spring, I know the time period is equal to 2 root over 2 pi, sorry, 2 pi root over k by m. Okay, this we know. So time period we know, even omega also we know, that is root over k by m. Okay, root over k by m. I'm sorry, this is m by k. Root over m by k. M by k. That is that, like that you can find out. Okay. But first of all, you have to actually find out what is this motion is, whether it is SHM at all. So to find out whether it is SHM, see, I'm just multiplying 2, okay, 2 sine square to make it 2 sine square. So like this, so 2 sine square omega t. So this I can apply, see, this trigonometric identity, cos of 2 omega t. Okay, 1 minus cos of 2 omega t. So now you look, cos of 2 omega t. Okay, so now, so this is actually the simple harmonic motion. See, any cos and sine, let it be, see, let this frequency be different, but you know, this is cosine, so cos omega t, sine omega t, this is actually representing an SHM. Okay, so once we know it is SHM, then rest of the thing is easy to do, right? So what is that? What we should do now? We have to actually find out here here actually the frequency of this oscillation is actually 2 omega. Okay, so 2 omega is equal to, see, I can write here 2 omega is equal to root over m by k. Okay, but what is this m by k? How to find out this k here? Okay, m by k. All right, see, I actually better to find this thing, like, see, we know like f is equal to minus kx. So in this case, what is this f? So then we go for like m dt x by dt square, right, is equal to minus kx, like that we go. So in this case, you know, in this case the force is mg, right? Mg is the force. Okay, so that force will be actually counteracted by k into, see here, this one is actually the amplitude. Okay, amplitude is this one. Okay, this much maximum amplitude it can actually displace. All right, so I can just write that ky is y0 by 2. The question was, see, y is measured from the lower end of the unstretched spring, then what is omega? So I have to find out omega. Okay, see, then see, g acceleration is actually k by 2m into y0 is the displacement, obviously. So what we are going to find out, I'm sorry, this is y0 is actually not the variable. I'm sorry, here actually the variable is this one, y0 1 minus of this. Okay, so this is the amplitude part. Okay, so actually when it is say at the, see, if I just take this simple pendulum, at the maximum displacement only you get the whole force or maximum force. So that is what we are just doing here, equating the maximum force, or mg is equal to this one. Okay, so from here we have to find out what is k by m. Okay, so let us find out what is k by m from here. Okay, so k by m will be, see, this 2g by y naught. Okay, then what is m by k? M by k is y naught by 2g. Okay, so here I'll put then, so m by k is actually, sorry, this m by k is equal to y naught by 2g. So square root of y naught by 2g. Okay, so this will be actually my omega. Okay, so let us see the options, whether I have done some mistake here. Two g y naught by 2g, yeah, it is all right. Let me cross check once again. I think I'm sorry. Actually, it is k by m, not m by k. It is k by m. I'm sorry. Sorry, this is, see, here I have written this wrong. So this is omega is equal to 2 pi root over, sorry, not 2 pi. Here only k by m. Okay. I'm sorry for the mistake. This was due to hurry. So k by m is actually 2g by y naught. Okay, 2g by y naught, that is actually omega. 2g by y naught. Okay, so I'll just repeat just to not confuse you. See here, we know this omega is equal to k by m, but what is k by m? We have to express in terms of this y naught and g. That is what we had to do. So k by m, we know this is actually for any spring, but in this case we have to write what is the force mg. So mg, and this will be exactly equal. See, this is the maximum force, and that maximum force is actually is seen where, at the maximum displacement. Okay, at this particular position. So now from here you have to find out k by m. K by m means 2g by y naught. Okay, so that is what we had to apply here. Okay, so thank you for your patience. I'll be concluding discussions here. Next day we'll be taking up few more problems from the same paper. So thank you for your patience for today.